back to Explained, where we like to take these kind of complex topics and break them down to something a little easier to digest.
Yeah, make them bite-sized, you know?
Exactly.
That's what we do here.
And today we are diving into algorithms and data structures.
Ooh, sounds intimidating.
It does sound a little bit intimidating.
Right, but I promise it's not.
But they're really the backbone of like everything digital that we use every day.
Yeah, think about your phone. The apps you use, the websites you visit, all powered by these things.
Yeah. So understanding them gives you like a peek behind the curtain
A little bit.
of how technology works.
Right.
So before we fully unpack these concepts, I want to start with a little thought experiment.
Okay, I like it.
Imagine you're searching for a specific book in a massive library.
Huge library.
Okay. How would you go about finding it without having to look at every single book on every single shelf?
Ooh, that's a good one.
I want you to share your strategies down in the comments.
Yeah, let us know.
We'd love to hear your thoughts on this. But back to our main topic. What exactly are algorithms?
So an algorithm is basically a set of instructions
Okay.
for solving a problem.
Okay.
It's like a recipe. You have your inputs, which are like ingredients,
Okay.
and then you have a sequence of steps that transform those inputs into your desired output.
Like a delicious dish.
Exactly.
I like that.
Yeah.
So what kind of digital dishes are we cooking up with algorithms?
All sorts.
Okay.
We're using them to sort data,
Okay.
to find the shortest route between 2 points, recommend products that you might like,
Yeah.
all sorts of things. The key is they provide a structured approach to solving a specific problem.
Okay, so it's not about a particular programming language. It's more about the logic.
Exactly. An algorithm can be implemented in any programming language.
Okay.
It's the underlying concept that matters.
Got it.
Yeah.
So what about data structures?
Okay, so data structures.
How do they fit into all of this?
Yeah, so just like you wouldn't store all of your belongings in one giant messy pile.
Right.
Computers need ways to organize data. Okay.
For efficient storage and retrieval.
Yeah.
So data structures are like specialized containers for information.
So like the folders and files on our computer.
Yeah, that's a good analogy for how we organize things visually.
Yeah.
But on a lower level, computers use structures like arrays,
Okay.
linked lists, trees, graphs,
Oh, wow.
to represent and manipulate data.
Okay, I'm starting to see how this connects. So we've got the algorithms, which are the instructions, and the data structures, which are like the containers for the information.
Precisely. And the interesting part is how these two concepts work together.
Okay.
So the choice of data structure can significantly impact the efficiency of an algorithm.
Okay.
Imagine trying to find a specific book in a library where all the books are randomly scattered on the floor
Oh my gosh.
versus a library with organized shelves and a cataloging system.
Yeah, that would be a nightmare.
Right.
The right organization makes a huge difference.
Absolutely.
So let's dive into these data structures a little bit more.
What are some of the key types that we should know about?
So one way to categorize them is by how they're organized in memory.
Okay.
So you have continuous versus linked structures.
Okay.
So continuous structures like arrays store data in one contiguous block, which can be efficient for accessing elements.
Okay.
However, they can be inflexible if you need to insert or delete elements.
So it's like having a row of houses and each one has a fixed address.
Yeah.
If you need to add a house in the middle,
Yeah.
it gets really complicated.
It gets messy.
Yeah.
Now, linked structures, like linked lists, are more flexible.
Okay.
They use pointers to connect pieces of data that are stored in different memory locations.
So it's like a treasure hunt
Yeah.
where each clue leads you to the next one.
Exactly.
I like that.
Yeah, so linked structures are more adaptable.
Okay, so what's the trade-off?
Well, while they offer flexibility, accessing specific elements in a linked structure
Okay.
might require traversing multiple pointers, which can be less efficient than directly accessing an element in a continuous structure.
I see. So it's like this balancing act
Right.
of choosing the right structure based on the task at hand.
Absolutely. It's all about understanding the strengths and weaknesses of each type and selecting the one that best suits the problem you're trying to solve.
This is giving me like a whole new appreciation for what goes on behind the scenes of every app and website that I use.
It's a lot.
Yeah.
It is.
Don't forget to follow Explained for more deep dives into fascinating topics like this.
Yeah.
You mentioned that the choice of data structure impacts an algorithm's efficiency.
Yes.
Can you elaborate on what we mean by efficiency in this context?
Sure. So in simple terms, efficiency refers to how well an algorithm utilizes resources like time and memory.
Okay.
So you might have multiple algorithms that solve the same problem, but some will be much faster or use less memory than others.
So it's kind of like choosing between two routes to get to the same destination.
Yeah.
One might be shorter and smoother, while the other might be longer and full of detours.
Perfect analogy.
And understanding how to analyze and compare the efficiency of algorithms is crucial, especially when you're dealing with large data sets.
Absolutely.
This is where things get really interesting. But before we dive deeper into algorithm efficiency, let's pause for a second and imagine you're designing a social media app.
Okay.
How would you design an algorithm to decide what posts to show users first? What factors would you consider?
It's a great question.
Drop your ideas in the comments. We're curious to hear your thought process on that one.
Yeah.
Okay, but let's get back to the basics of measuring efficiency.
Okay.
One common way to do this is to analyze the number of steps an algorithm takes to solve a problem.
Right.
So are we literally counting lines of code?
Not exactly. We use a simplified model called the RAM model,
Okay.
where we assume each basic operation, like adding two numbers or comparing two values, takes a unit of time.
Okay.
We then analyze how the number of steps grows as the input size increases.
So if an algorithm takes 10 steps for an input of size 10 and 100 steps for an input of size 100,
Yeah.
that would indicate a linear relationship.
You got it. And that brings us to Big O notation,
Ooh.
a powerful tool for describing the growth of an algorithm's runtime as the input size gets very large.
This is where it might start to sound a little technical,
Yeah,
but I think it's important to understand.
I agree. So Big O notation helps us abstract away from specific numbers of steps and focus on the overall trend. It allows us to compare algorithms at a high level
Okay.
and understand how their performance scales with increasing data.
So instead of saying an algorithm takes 10 steps or 100 steps,
Right.
we'd use a notation like O n n to represent linear growth,
Yeah.
or O log n to represent logarithmic growth where the runtime increases much slower.
Exactly. And those differences in growth rates become incredibly important when you're dealing with massive data sets.
This is blowing my mind. I'm starting to realize just how much thought and complexity goes into what seems like very simple tasks on our computers and phones.
It's a lot.
So how do we go from this very theoretical understanding of Big O notation to actually choosing the right algorithm for a specific problem? What factors are we thinking about?
That's a great question, and it's something we'll explore in more detail in the next part of our deep dive.
Okay.
We'll look at real-world examples of how different algorithms are chosen and optimized based on the specific problem they're trying to solve.
I can't wait. It's amazing how understanding these kind of abstract concepts can give us a whole new appreciation for the technology that we use every single day.
Absolutely.
And we'll be right back after a short break.
Welcome back. Before the break, we were talking about Big O notation and
Okay.
how it helps us analyze the efficiency of algorithms.
Yeah.
So now let's dive into some specific examples
Okay.
of these growth rates and what they actually mean.
Okay, so let's start with logarithmic growth, which you mentioned is very efficient. Can you give me a real-world scenario where this type of algorithm really shines?
Sure. So imagine you're using a search engine like Google.
Okay.
When you type in a query, the engine needs to find relevant web pages among billions of possibilities.
Yeah.
A naive approach would be to check each page one by one.
That would take forever.
Yeah, it would be incredibly inefficient, especially given how quickly we expect those results to appear.
Right.
So that's where logarithmic growth comes in.
Okay.
Search engines use algorithms like binary search,
Okay.
which have logarithmic complexity.
Mm-hmm.
So think back to our library analogy.
Okay.
Instead of checking every single book, you could start in the middle.
Okay.
See if the book you're looking for comes before or after that point,
Right.
and keep dividing the remaining search space in half.
So even with billions of web pages, a logarithmic search can narrow down the possibilities very quickly.
Precisely. That's the power of logarithmic growth.
That's pretty cool.
Yeah.
Okay, so let's contrast that with linear growth.
Right.
What does that look like?
So imagine you're reading a book.
Oh,
You have to read each page sequentially.
Right.
And the time it takes to finish the book increases linearly with the number of pages.
Okay, that's pretty intuitive. I get that one.
All right.
What about quadratic growth?
Quadratic growth.
You mentioned it gets less efficient as the input size increases?
Yes. So think about social networks.
Okay.
Let's say you have a group of friends
Mm-hmm.
and you want to see all the possible connections between them.
Okay.
As the group size grows,
Yeah.
the number of connections increases much faster.
Right.
Kind of like a chain reaction.
Yeah, like the handshaking problem we talked about earlier.
Yeah.
where everybody has to shake everybody else's hand.
Right. And some sorting algorithms like Bubble exhibit this type of behavior.
I see.
Yeah.
Okay, and then we have the least desirable but sometimes unavoidable.
Exponential growth.
Exponential growth.
Yeah.
What does that look like?
So imagine you're trying to find all the possible routes between cities on a map. As the number of cities increases, the number of possible routes explodes exponentially.
So it's like a branching path where each decision leads to a ton of new possibilities.
Precisely. And some problems like breaking encryption codes or finding optimal solutions in complex systems often involve this type of complexity.
I see. So this is really eye-opening. It seems like choosing the right algorithm is really important, especially when you're dealing with these massive data sets.
It's all about understanding the trade-offs.
Okay.
Some algorithms are easy to implement, but they might be inefficient for large data sets.
Right.
Others might be more complex, but offer much better performance.
So it's not just about finding an algorithm that works.
Right.
It's about finding one that works well and scales.
Exactly. And that's where a deep understanding of data structures and algorithms becomes super valuable.
Okay, so let's get back to data structures for a second.
Okay.
Earlier, we talked about continuous and linked structures. But are there other ways to categorize these containers for data?
Yeah, you mentioned arrays and linked lists. What about those other structures we mentioned, like trees and graphs?
Yeah, where do those fit in?
So trees and graphs are nonlinear data structures,
Okay.
which means they don't follow a simple sequential order like arrays or linked lists. They're used to represent hierarchical relationships or complex networks of interconnected data.
So a tree structure could represent something like a family tree.
Yeah.
Or the files on a computer.
Exactly. So in a tree, each element has a parent-child relationship with a single root element at the top and branches extending downwards.
Okay.
Now, graphs, on the other hand, are more general.
Okay.
They consist of nodes, which represent entities, and edges, which represent the relationships between them.
So a social network could be represented as a graph, where each person is a node.
Yeah.
And their friendships are the edges.
Precisely. Graphs are incredibly versatile.
Yeah.
And they're used to model all sorts of real-world phenomena.
I could see that.
From social networks to transportation systems to the flow of information on the internet.
This is really fascinating. It's amazing how these abstract data structures can represent so many things.
It is.
It seems like choosing the right data structure is just as important as choosing the right algorithm.
Absolutely. The choice of data structure can impact not only the efficiency of an algorithm, but also the clarity and elegance of your code.
Yeah.
Just like a carpenter wouldn't use a hammer for every task.
Right.
A skilled programmer chooses data structures that best suit the problem at hand.
So it's all about having the right tools and knowing when to use them.
Exactly. And that brings us to an important point.
Okay.
Understanding these concepts isn't just about memorizing definitions or writing code. It's about developing a way of thinking.
Yeah.
A mental model for how information is organized and processed.
So it's about becoming fluent in the language of the digital world.
Precisely. And that fluency empowers you to understand how technology works at a deeper level, to make informed decisions about the tools you use, and even to create your own innovative solutions.
I love that. It's about moving from being a passive user of technology to an active participant.
Exactly.
And really understanding the magic behind the curtain.
It is.
Don't forget to follow Explained for more deep dives like this one.
Yes.
Now let's tie all of this back to the real world.
Okay.
We've talked about algorithms and data structures in a pretty abstract way.
We have.
But how do these concepts actually show up in the technology that we use every day?
That's a great question. It's easy to get lost in the technical details.
Yeah.
But I think it's important to connect these ideas back to our daily lives.
Absolutely.
Okay.
So let's start with something that we use all the time, search engines.
Okay.
We talked about how algorithms like binary search make it possible to find information so quickly. But there's a lot more going on behind the scenes.
There is.
So it's not just about finding a web page that has the keywords I typed in.
Not at all. Modern search engines use incredibly sophisticated algorithms to rank those search results, taking into account hundreds of factors like relevance, authority, freshness, user location, and even your past search history.
So it's like a personalized information filter.
Exactly. It's tailoring the results to what it thinks you're most likely to find useful.
That's kind of creepy, but also kind of cool.
Yeah.
And that personalization is all powered by algorithms.
It is by complex algorithms that analyze huge amounts of data to understand your preferences and your intent.
It's mind-boggling to think about the scale of data processing that happens every time I do a Google search.
It's a lot.
What are some other examples of this?
Well, think about social media.
Okay.
The algorithms they use determine what posts you see in your feed, who you get recommended as a friend, and even what ads are targeted at you.
Yeah, that's something I think about a lot. These platforms seem to know me better than I know myself sometimes.
It's all about data and the algorithms that process it.
Okay.
The more you interact with a platform, the more data they have about your preferences.
Right.
And the better they can tailor your experience for better or for worse.
And it's not just social media, right?
Now, these concepts are everywhere.
Like where else?
Think about online shopping.
Okay.
Recommendation algorithms suggest products you might like based on your browsing history and past purchases.
Yeah.
Or navigation apps that use algorithms to find the fastest route, taking into account traffic conditions, road closures, even your preferred mode of transportation.
It really is amazing when you start to connect the dots.
It is.
These very simple tasks that we do every day are powered by incredibly complex systems.
Right, and understanding these systems, even at a basic level, empowers us to make more informed decisions about the technology that we use.
Exactly. It's like becoming literate in the digital age.
Yeah, it's also important to remember that these technologies aren't neutral tools.
Okay.
They're created by people, and they reflect the biases and values of their creators.
That's a really important point. As we become more aware of how these systems work, we also need to be more critical of their potential impacts on society.
Couldn't agree more. It's essential to have open discussions about the ethical implications of these algorithms.
Yeah.
And to advocate for transparency and accountability from the companies that are developing them.
Well, I think we've covered a lot of ground today.
We have.
From these abstract concepts of data structures and algorithms to their real-world applications and even some of the ethical issues that they raise.
Yeah. Hopefully it sparked your curiosity to learn even more.
Absolutely. But before we wrap up, I want to leave our listeners with one final thought.
Okay.
We've talked about how algorithms are used to personalize our experiences online. But what are some of the downsides of this? Could it lead to filter bubbles or reinforce existing biases? Let us know your thoughts in the comments.
Yeah, that's a great question to ponder.
As we become more reliant on these algorithms to filter and curate information, I think it's really important to be aware of those potential consequences.
Absolutely.
Welcome back to Explained. Before the break, we were looking at how algorithms are shaping our experiences online.
Right, with things like search engines and social media.
Yeah, but let's shift gears a little bit and think about some other areas where algorithms are quietly at work behind the scenes.
Okay, so let's talk about finance for a second.
Okay.
Algorithms are the driving force behind high-frequency trading, where computers are making thousands of trades per second based on this, lightning-fast analysis of market data.
That sounds intense.
Yeah.
So it's not just about humans making decisions on Wall Street anymore.
Not entirely. Algorithms can spot patterns and react to market fluctuations much faster than any human trader could.
Wow.
So this leads to both opportunities and potential risks in the financial system.
Yeah, that's a whole other deep dive waiting to happen.
Right.
But what about areas beyond the digital world? Are algorithms starting to make their way into the physical world too?
Absolutely. So consider self-driving cars.
Okay.
They rely heavily on algorithms to perceive their surroundings, make decisions, navigate safely. It's this complex interplay of sensor data, machine learning, and real-time processing.
Yeah, it's kind of wild to think about algorithms being responsible for driving us around in the future.
It is a lot of trust we're putting in these algorithms.
Yeah, it's not just transportation. Algorithms are transforming healthcare as well.
Right. They're being used to analyze medical images, diagnose diseases, even develop personalized treatment plans.
It really is mind-blowing when you see the connections.
It is.
These seemingly completely different fields are all being reshaped by this power of algorithms.
Yeah, and as these technologies continue to evolve, it's really important to think about the potential implications.
You're right, we've touched on some of the ethical considerations, but are there other challenges or concerns that we should be keeping in mind?
Yeah, one key challenge is making sure that these algorithms are fair and unbiased.
Oh.
So if the data used to train an algorithm contains biases, those biases can be amplified and perpetuated by the algorithm's decisions.
So it's not enough to just create an algorithm that's technically sound.
Right.
We also need to think about the social and ethical implications.
Exactly. We need to make sure that algorithms are being used responsibly, transparently, and in a way that benefits society as a whole.
I think that's a really important point to emphasize. So to wrap things up, I think we've covered a lot of ground today.
We have.
We've explored these fundamental concepts of algorithms and data structures, seen how they're being used in all these different fields, and talked about some of the opportunities and challenges that come along with them.
Yeah, hopefully this has given you a new perspective on these sort of invisible forces that are shaping our world.
Absolutely. And I think a much deeper appreciation for the complexity and also kind of the beauty of these computational creations.
Yeah.
So to our listeners, what are your thoughts on all of this? Have we sparked any new questions or ideas for you?
Yeah.
Share your reflections down in the comments below.
And if there's a topic that you'd like us to explore on a future episode of Explained, be sure to let us know.
Yeah, we're always looking for new avenues to explore. Until next time, keep questioning, keep learning, and keep exploring this amazing world around us.